Welcome to this video podcast. My name is Cyril Noger. Today I will explain you in more details about the MS2090A real-time spectrum analyzer function and more especially the display. First of all, let's make a brief summary and comparison between the RTSA and a conventional spectrum analyzer. As shown here, spectrum analyzers and vector signal analyzers are far different compared to a real-time spectrum analyzer. One of the issues a spectrum analyzer has is the fact that it has some blind times. It's not able to capture elusive and transient signals as it's not sweeping fast enough. When we consider RTSA, it's able to measure any kind of signal without any gap in the measurement time. Since the amount of measurements performed per second by the RTSA is far bigger than the display update rate of the unit itself, it requires an advanced display method to process all the data. This slide shows why a spectrum analyzer sometimes is blind. In fact, when a signal is not present all the time and as long as the local oscillator is required to be swept, there are some chances that the signal won't be seen on the display. So on this slide we show red signals, frequency carriers that are present in some moment of the time. And one of the issues is that if this frequency carrier is not seen by the spectrum analyzer as long as the local oscillator doesn't have the proper frequency inside the spectrum analyzer, the carrier won't be seen. On this drawing, if we represent 4 carriers in frequencies and a time axis and vertical, we see that the local oscillator takes some time to sweep across the band from frequency 1 to frequency 4, for instance. And if the RBW doesn't scans the frequency at the correct time when they are present, it won't be seen on the display. So in that case, the example here shows that only frequency 1 and frequency 2 would be seen on the display since the local oscillator and the RBW settings were correct at the moment of the time these carriers were present. The frequency 3 and frequency 4 carriers are not seen by the spectrum analyzer since during the sweep we consider here the RBW's filter has not seen this F3 and F4 carriers. The fact that some frequencies or carriers can't be seen on a spectrum analyzer represents one kind of blindness of a spectrum analyzer, as depending on how occurrent these frequencies are, so, the spectrum analyzer may miss some information during a sweep. So let's see briefly why this phenomenon occurs. Modern step-tuned FFT spectrum analyzers have local oscillator that needs to be tuned in discrete steps in order for the spectrum analyzer to go across the frequency band from the frequency 1 to frequency X that needs to be swept. However, in order to get some meaningful measurements, the local oscillator must stay parked until the FFT has enough samples. So this is what is represented on this drawing, where 3 stops are considered. And if we consider the time it takes to acquire samples, it's really fast, but then the FFT needs to be processed. And as long as the FFT is not processed or not finished, it cannot go to the next step. In addition, this drawing also highlights the fact that between two sample acquisition and FFT processes, there is a very small gap between two processes. This represents one weakness of spectrum analyzers, as in between two acquisitions, no measurements can be done. If we compare a spectrum analyzer to an RTSA, one of the big differences is the fact that for RTSA, the local oscillator is stationary. One other difference that can be highlighted here is the fact that the RTSA is able to acquire samples one after the other without any gap in between each of them, and it is able to make its FFT calculations at the same time in parallel. As a consequence, there is no data that is lost, so no measurements are lost, no gap. Having said that, the difference between the spectrum analyzer and the RTSA is that the RTSA would be band limited in terms of span, as it cannot process, let's say, tens of gigahertz at a time, whereas the spectrum analyzer can. huge amounts of data would be processed and acquired by the RTSA, so it requires a new way to display the information on the screen, and this is what we'll explain right now. So how are the measurements of the RTSA displayed on the screen? As we've understood from the previous slides, very large amounts of data will be processed by the FPGA and DSPs of the RTSA. As a consequence, the RTSA is introducing a new way of displaying measurements on the screen. This is called density spectrum, and it's represented by various colors representing a heat map. As shown here on top right of the slide, the data are represented in color so that the heat map could be understood by the user. So the more the information goes to the red, the more frequent these amplitudes are seen, and the more the data goes to the blue or dark blue, the less present the data or amplitudes are seen. To perfectly understand this heat map concept, let's consider 3 consecutive FFTs. To make the example simple to explain, let's say that the FFTs have only 5 data points each. By analogy, if we could say that each data point of the FFT could be considered as a pixel, these pixels would be numbered as 1 every time the pixel is hit. Since these FFTs are processed one after the other, it means that the signal is changing over time. So this is why every FFT is different from the other one. To create the heat map frame, the RTSA process will sum up the number of times each pixels have been hit. So this is why you can see on the heat map frame in the middle of the slide that some pixels have been hit 3 times, other pixels have been hit 2 times, and other pixels have been hit only 1 time. These numbers represent the occurrency of the amplitudes. Having said that, the RTSA will now assign a color to the occurrency. So as I said, the more it goes to the red, the more present it is in time. The more it goes to the blue, the less present it is in time. As seen on the drawing, on the display, the pixels that have been hit 3 times are represented in red since they are more occurrent than the other ones, and the pixels that have been hit 2 times are represented in yellow, and the pixels that have been hit only once are represented in blue. So this is allowing to make the difference between very present signals in time and transients. Elusive or transient signals would be color-coded in blue, as this means that they are not really present in time. As hundreds of thousands of FFTs are processed per second by the RTSA, we need to find a way to let the user understanding about the persistence or how old are the transients. Every time a FFT is processed by the RTSA, a new heat map is generated by the RTSA, but the human eye has no way to go as fast as the FFTs are processed. So to generate a meaningful display, we have to introduce the concept of variable persistence to help the user to see all the information on the screen. Along the FFT processes, if considered pixel or amplitude is not hit or not seen once again, it should become transparent. This color fading would go from the color code to a transparency depending on the acquisition time. Both the acquisition time and persistence time are determined by the user directly in the menus of the RTSA. We can also note that persistent state can be defined between variable and infinite, depending on really what the user wants to see. In case this would be chosen as infinite, the consequence of that would be no fading of the data color. This is very helpful to understand, for instance, about the spectrum occupancy in a given frequency band. To understand the variable persistence concept, let's say that the acquisition, for instance, would be 50 milliseconds long. If the user has chosen 200 milliseconds as a variable persistence time, this will have a consequence on the persistence refreshing rate. Considering each heat map frame or acquisition, a display is to be created and refreshed compared to the previous one. For the display from one step to the other, The main difference will be on the pixels themselves. If the pixel for a given amplitude is not hit anymore, it will fade in color. For a pixel on a display, if an amplitude is measured, then the pixel will be assigned with a new color. After waiting for 200 milliseconds, since this is the variable time that has been chosen for the persistence display, the display on itself will be refreshed and will correspond to the next heat map. If now the persistence has been chosen as infinite instead of variable, the same 200 milliseconds will be kept in memory, but no change won't occur between the different displays. So the infinite persistence will remain the same and will show all the pixels that have been hit since the beginning of the measurement. No fading is applied on colors, but just new colors in case new amplitudes are hit. Now that the heat map and the color codes have been understood, and including the persistence concept, here is an example of what a frequency band could look like if elusive or transient signal exists in the middle of constant signals. In this particular example shown here, we can see that the noise is more present than any other kind of frequency carrier, as the noise is color-coded in red, which means it's present almost all the time, but as it is random, it's not having the same amplitude all the time. To help the user to understand even more what's happening to the frequencies he's having a look at, we can add the spectrogram color code on top of the RTSA heat map. In that case, the spectrogram, also called waterfall, will assign a color to every amplitude, and as long as the amplitude is high, it goes to the red, and as long as it goes to the blue, it means that the amplitude is really low. The spectrogram trace is then built acquisition after acquisition, and this is what is represented on the right of the screen, which sometimes looks like a waterfall, so this is why it's called waterfall. This waterfall display is very useful to understand about the behavior of the carriers, understanding about the consistency in time of a carrier or any frequency drift and so on. As the time is represented in vertical axis, we have a kind of history of what happened in the frequency span. Being able to get both the RTSA color code and the spectrogram on the same screen is really important to understand about the behavior of signals. The elusiveness of transients or short carriers can even be seen on the RTSA and spectrogram, since as looking at the arrows by now, we can understand about which frequency occurred and when. To conclude this presentation, let's have a look at a comprehensive frequency band that shows lots of information. The current measurement has been recorded in the 2.4 GHz ISM frequency band. This band hosts Bluetooth and Wi-Fi signals. As we can see here, the noise is more present than any other kind of signal. As explained in the previous slide, in the RTSA menu, it's possible to have a look at both the RTSA heat map and the spectrogram, as shown here. The spectrogram at the bottom of the screen is showing the amplitude variation across the time. Thanks to the persistence display, we've just seen that a carrier has just swept across the band. This is also noticeable on the spectrogram display. The current persistence time is now 5 seconds, and it can be changed if the user wants it to. We can move it to the minimum, which is 0, and then this means that there won't be any persistence on the density spectrum display. The change of this persistence parameter doesn't affect the spectrogram, it just affects the density spectrum on top of the screen. For sure, the user can change this persistence time anytime he wants. The user has the ability to change the density resolution. In the RTSA menu, it's possible to go from high resolution, which provides a probability of intercept in that case of 6 microseconds long, to change the density resolution to normal mode, which provides a probability of interception of 3 microseconds long. So this affects the display, as you can see actually on the screen. The value of this POI is very important to understand for an RTSA. If we take the example of this 3 microseconds long POI with the current settings on the RTSA, it means that the RTSA will be able to measure with 100% accuracy the amplitude of very short signals like 3 microseconds long. The MS2090A is specified for a 2.055 microseconds long probability of intercept, which means that the MS2090A will be able to capture the amplitude of very short, narrow signals like 2 microseconds long with 100% accuracy. As shown here on the unit, the combination of both the RTSA display and the spectrogram display are very useful for a very accurate measurement. We now have reached the end of this presentation. I hope it was instructive for you. If you have any requests about the MS2090A, please do not hesitate to contact your local Anritsu office or to visit us on www.anritsu.com. Thank you.